this is the 21 and we will be presenting on transfer functions today. So a transfer function is basically a mathematical representation of a linear time invariant system in the Laplace domain. They're basically giving us the ratio of the output to the input. And so it can help us represent dynamic behavior of systems such as control systems, mechanical systems, electrical circuits, without actually solving differential equations directly. So you are able to tell whether the system is stable or not. You can determine the rise time, settling time, eventually steady state error. So many things using transfer functions. So today we're going to use the transfer function to relate capacitor voltage to the input voltage, where we have the resistor, the inductor, and the capacitor in series. So we'll be using two methods, the Laplace method basically to get the transfer function. So we convert it from the time domain to the S domain. And then we'll also be using signal flow graphs and then the Mason flow. And we'll compare both methods, show you the ups and downs, and basically give you the transfer function.
In a given circuit, we have our input voltage to be V of t. There are also three circuit elements which are connected in series with each other. There is an inductor, resistor, and capacitor. There's also an output voltage, that is the voltage across the capacitor, which is VC of t. Now, in order to calculate the overall transfer of the electrical network, we first have to convert it into the S domain, that is the Laplace domain. In so doing, we realize that the voltage, the input voltage, that is the V of t, now becomes V of S. The capacitor, that is the C, now becomes 1 over SC, and the inductor L becomes SL. The resistor, however, is the same in the Laplace domain. Now, since the circuits or the circuit elements are in series, the total impedance is by simply adding the impedances in Laplace domain. You can also go ahead and calculate the output voltage, VC of S, using the voltage divider rule since the elements are in series.
So I would like to discuss on how we're able to make the voltage divider setup, right? So in our question here, we are told to find the transfer function that's relating the VC, which is the voltage in the capacitor, to VS, that's the source voltage, right? So in order to find this, we need to create an equation that can relate both of them, right? So looking at this, we can see that in our circuit we have resistor, that's a resistor, we have an inductor, and we have the capacitor for which we are looking for the expression for, right? So we can use the voltage divider rule, that's as a way of finding the voltage drop in that capacitor, and use that to relate it to the source voltage, right? So per the voltage divider rule, the total voltage in the circuit is, let's say, the source voltage, that's Vs, right? So per the voltage divider rule, the voltage in the, or let's say the voltage drop in the capacitor is given as what? The voltage in the capacitor is given as what? The total impedance in the capacitor over the total impedance in the whole circuit, that's a sum of the impedance in the capacitor, in the resistor, and the inductor. All of it times the total voltage, that's the source voltage, right? So taking their Laplace transforms, you can see that the impedance in the capacitor has its Laplace transform to be 1 over SC, right? And the impedance in the resistor has its Laplace transform to be R, and the impedance in the inductor has its Laplace transform to be SL, right? So you can see that the total, that the voltage divider rule, when they're giving us an expression which is VC is equal to 1 over SC all over R plus SL plus 1 over SC times the source voltage, that's Vs, and I'll give you the setup for the voltage divider. Thank you very much.
Okay, my name is Ahimfo Michael. In this part, I'm going to talk about how to simplify the voltage divider equation. The first thing we have to do is multiply the numerator and the denominator by SC so that we can clear the function. So when we multiply the numerator by SC, we are going to cancel SC. Then we'll get 1 at the numerator, then SC at the denominator. So the resulting equation will be H of S is equal to 1 over SC into bracket SL plus R plus 1 over SC. Then you are going to open the bracket by multiplying SE throughout. So the resulting equation, which is h of s is equal to s squared plus c plus src plus 1, is the overall transfer function. Thank you.
You can also use a signal flow graph and then apply the Mason's gain formula to obtain the transfer function. Now I'll be constructing the signal flow graph for this system, and to do that, start from the equations you already obtained in the Laplace domain. So we write the branch current equation using Ohm's law across the resistor and then the inductor. Now, since they are in series, their total impedance is going to be R plus SL. So the branch current therefore becomes I of S is going to be equal to VI of S minus VO of S all over R plus SL. That's the voltage difference between VI of S and V of S divided by the total impedance. We can also rearrange it, and then it becomes I of S is going to be 1 over R plus SL multiplying VI of S minus 1 over R plus SL multiplying V of S. So now we move on to the capacitor voltage equation, and this output voltage is simply going to become the voltage across the capacitor. That's going to be V of S is equal to 1 over SC multiplying I of S. Now that you have these two equations, they are in a form suitable for constructing our signal flow graph. So now we have three variables, Vi of S, I of S, and the V of S. We are going to use this to construct the SFG. Now from the first equation, we draw a branch from Vi of S to I of S with gain 1 over R plus SL. Then also draw a feedback branch from VO of S back to I of S with gain negative 1 over R plus SL. This is going to be our negative feedback path. Now from the second equation, we also draw a branch from I of S to V of S with gain 1 over SC. Now at this point, we have our SFG and it's complete. You can clearly identify one forward path from the input to output and then one feedback loop in the system.
Now we apply this new gain formula. First, we find the whole path. There is one more forward path there to be. This gain P1 is 1 over R plus S multiplied by 1 over S. Next, we find the new gain. There is one loop on by gain from I to B and back to I. The loop gain L1 is negative 1 over R plus S multiplied by 1 over S. Now calculate delta. Delta equals 1 minus the sum of loop gains. Since there is only one loop, delta equals 1 minus L1. So delta becomes 1 plus 1 over R plus S del times S. There are no non-touch loops. Next, delta 1 is equal to 1 because the loop touches the point 1. Now we are finding this V over I equals V1 divided by delta. That's the group, and you get V over VI equals 1 divided by S squared equals FSC plus 1. This is the final transfer function. Thank you.
Since my colleagues have already explained both methods, I'll focus purely on comparing them. The first method, voltage divider rule. This is quick and intuitive for simple series circuits like this RLC circuit. It only works for passive circuits with clear series structure. The second method, signal flow graph. This is systematic and visual and shows signal paths and feedback loops clearly. It requires drawing the graph and using Mason's gain formula. The key difference between the two is that voltage divider gives you the answer through algebraic manipulation, whereas signal flow graph gives you insights into how signals propagate through the system. The question is which to use. For this simple series circuit, both work equally well, but for complex systems with multiple loops and feedbacks, signal flow graph is essential, whereas voltage divider rule is impractical. In short, voltage divider gives you speed and simplicity, whereas signal flow graph gives you insight and versatility. Thank you.